Hi, welcome back. This is the video in continuation with my earlier videos. These are typically my prerequisite videos for the courses I conduct, both over online and in classroom. So today we are going to discuss about the network layer. So you can call it as an IP layer of the TCP IP. So my name is Samba. I work for Career Booster Technologies, and I am the trainer here. So I do undertake training courses on the networking, be it testing, network protocol testing, or the certification courses like CCNA and CCNP, right? In addition, I also do courses on the 3G, 4G, and 5G mobile technologies. So that's just a reintroduction of myself. Okay, so as I said, today's discussion will be about the network layer in the TCP IP model. This is in continuation with the discussion we had on the application and transport layers earlier. Now, to understand the network layer easily, I think you should know how the postal system works, all the mail system works in general. I hope most of you know how it works, right? So this is a kind of a depiction of the postal network showing you have a source, where the letter is posted. I'm just getting the pointer in place, where the source is there, where the letter is posted, and you have a destination, right? So there's a source and there's a destination. Now, what we all know very well, actually, that was there in my TCP IP introduction video also, that the letter that is posted in the post box contains address written on it. So without any address, the letter can't move forward, right? So once the letter is ready to be posted, so it has an address on it, and then someone comes out of this house and drops it in the post box. So what happens next? Someone picks it up right from the post box and then takes it to the nearest post office and then sorts it out. So what's basically what he does is he reads the address. Once he reads the address, he knows where to put forward. So all you did, actually, looking at the destination, you put it in the post box and you walked away. So that's your job is done. Similarly, a postman, when he picks it up and then passes it to the next post office or next hop, okay, that person's job is done. And in the new post office, someone else will see that address and keep forwarding it one after the other till it reaches the destination, right? No matter what path a letter can take, if you really see this particular setup, the letter can go through any path. So probably it can go like this or it can go like this and all that. Yet the letter will never get lost. Why? Because there is an address on it. And all the people here in the post office, no matter who receives it, are capable of interpreting that address, understand where the destination is. Once they know where the destination is, they identify the next hop. So they may not directly go to the destination and then hand over the letter personally, right? All they need to do is read the address and pass it to the next hop, right? For example, if you see a particular path like this, just watch the bit of an animation on there. So this particular letter has gone through a certain path. So what happened at each of them? They fundamentally looked at the address, identified the next hop, and then forward it to that next hop. Simple, right? And everyone does this job. As a result of these combined actions by each post office, the letter has reached the destination. As I said, since the letter contains address on it, no matter what path it can take, it still reaches the destination. Just as an example of it, I'm just showing a different path. Now that is the capability the internet layer will add to the packet under the TCP IP. So it puts that address on it, right? The packet has come from application and transport. When it is handed over to the IP layer or network layer, the network layer adds an IP header, and one of the most critical components of that IP header is the source and destination addresses. Who is sending and who is the intended recipient? Who is the recipient? By these two values added to the packet is free enough to take any path in the network in reaching the destination. Every post office or every network element like router clearly able to understand and interpret the IP header. By looking at the addresses, it identifies the next hop, which could be a router, another router, and then forwards it. ultimately there will be the last hop reaches and it is delivered to the destination, right? So that's exactly IP layer works. I think somewhere in my videos I would have told you, if not I'm telling you now, fundamentally any switch or router in the network has one basic bread and butter job to do, and that is nothing but forwarding the packet towards the destination, right? And in the network layer, this is one identity, the IP address is one identity which will make many layer 3 devices or a routing function, routers, to forward the packet. So they use the IP address to forward the packet. And nothing can be a better example than the postal system. So what is network layer after all? Okay, it specifies how packets travel end to end over the TCP IP network, even if it has to go through multiple hops and multiple LAN and WAN links, no matter. Just because of that address is mentioned in the packet, it never gets lost, right? So there are two options for you in terms of how this address is put into the IP header. So you have a 32-bit format, which is IPv4. You have a 128-bit format, which is an IPv6. So we are going to discuss about that in the coming slides. Okay. So IPv4 was the earlier version of the Internet Protocol, still predominantly used all over the world. But at some point it was felt that we are running out of the addresses. Okay, because every host machine or every these days I can say things, right, because we are hearing about Internet of Things. If it wishes to be on the network, it should have a unique IP address. Now, to some extent, so these unique vertical addresses are not possible beyond a point. So there was a time where people felt that we are running out of the unique addresses, so the IPv6 format came in. But thanks to some of the services like network address translation or port address translation, somehow the shortage was overcome in a significant way. So that's the reason the migration to IPv6 was not, as rapid as any other migration. Still a large amount of machines all over the world are still working on IPv4 and not IPv6, right? In any case, we are going to discuss about it, and IPv6 is catching up slowly. It's growing its presence. So we will be going to discuss all that in the coming slides. So what the network layer focuses on, it focuses on routing the data in a form of IP packet from source host to the destination host. Imagine in one of my discussions, when I was showing the encapsulation, a datagram, once it is fitted with the IP header, it is referred as a packet. And this takes to a discussion where once upon a time, when I was younger, I used to really discuss this circuit mode communication, packet mode communication. And the huge difference was in a packet mode communication, every packet has a from and to address fitted into that so that it can go independently through any path to the destination. Not only that, whatever the physical media that is being used can be shared by many other users, because each packet has its bearings, from and destination is there. So they can go together, yet none of the elements can get mixed up. They can easily sort out the packets, read the IP header or the network layer and put to the destination. So once the IP header is fitted, we start referring as a packet. So in a general networking terminology, once you say a packet, be rest assured that the IP address is put on it or is written on it. So it relies, of course, on the lower layer. So IP layer to IP layer communication between the source and destination is a logical connection. So obviously, once the IP header is done, it has to hand it over to the data link layer below, and the data link layer will hand it over to the physical layer. So it depends on the lower layers to do the physical transmission, right? Quite simple to understand. And finally, like I said, it's all about logical details. So the connection between two IP layers of destination host is all about logical in nature. So this is the header which it attaches. This is like an overhead, right? So once it gets the information from the TCP layer, this is what the information gets added. And what you're seeing currently is an IPv4 header. So I know I didn't put the heading exactly, but it's an IPv4 header. So we have different fields like version length, distinguished services field. We have a packet length, identification, etc., and more importantly, source and destination addresses. So let's briefly understand each of this element. What do they do? Why it is required? Okay. So it goes like this. So the first one you have is the version. Now what is the version? It tells you whether it's an IPv4 or IPv6. So since this is an IPv4, obviously it has a value of 4. So it's a version 4, so that's why it's called IP version 4. So it tells you this is an IPv4, which is a 32-bit format. Next you have like length. Length is nothing but the length of this header, which is expressed in word. You know what is a word? Word is 32-bit. So bit is 1, you have nibble which is 4, which have a byte which is 8 bits. So you have like 32-bit words. So number of 32-bit words in the header, so that's what it says, and its length is 4 bits. Just to tell that once the header has started, it knows how long the header it is, and then you have a means to know this portion is the header and rest follows is the user data. Then happens what you call the distinguished services. There are like applications like voice and other which are time sensitive. So some application cannot afford their packets to be buffered for a very long time in any of the routers or network elements, and also they don't want to stand in a queue and then result in some sort of a loss of a data or a loss of the purpose, if I have to say that way, from an application point of view. They also cannot go in any sequence, they have to go in a certain sequence, and also like cannot afford to have a delay. Because for example, if a voice is there, I am speaking now, other person should listen now. There is no delays should be happening in between. So how does anyone would know? They would know by understanding, saying that, okay, hey, this is a voice packet, I can't treat it with on par with any other data packets, which are okay. Like you have downloading some file or something which may not be time sensitive. It's okay to have some delays here and there. It can go out of sequence or whatever is it. It doesn't matter there, but in a real-time communication, it matters. So to just distinguish that, that's how this field is there. And one example I can take is perhaps handling an emergency case in a hospital, right? A patient arrives somehow in a critical condition, and there are other patients whose condition may not be that serious, maybe some smaller issue. So what do the hospital staff or doctors would do? So they would attend to the critical patient first, because that situation is far more serious and cannot afford that patient to, for example, wait. Okay, so that's how this is. So this distinguishes the services. So it is just gives that much more importance to it and then takes it up on a priority. Then comes the packet length. So this is a 16-bit value of the entire packet. This is not the length of the header, whereas this was the length of header, right? Now this is nothing but the entire packet. Okay, it defines the entire packet including its header and data in bytes. Okay, so the maximum can be about 65,535 bytes, and that's nothing but the maximum value of a 16-bit word. So if you really see the decimal equation of a 16-bit, the maximum is 65,536. So that's the length actually. Followed by you have identification. So this is identifies a group of what do you call fragments. Why I'm talking about fragments? Because later when I cover the layer 2, you will understand this even more better. Normally what happens when the application sends the data to the what you call the IP layer, and IP has to forward it to the data link layer, right? In the data link layer, for example, if you are using Ethernet, IEEE 802.3 protocol Ethernet says my maximum capacity I can take is at a time is 1500 bytes. Okay, now when you have a 1500 bytes, the IP layer will fragment the original data. He said, okay, I can't put this entire huge packet onto the data link layer, because the data link layer threw up his hand saying that this is what the maximum I can do it, right? So what it does, it just fragments it. So you have fragmentation done. The whole big data is chopped into smaller fragments and then sent each out one by one. Now later in the physical media, they may get mixed up with other packets which may have something else. How does the recipient will gather all these fragments together to reconstruct the original datagram? So they need to have an identity, right? So this fellow is UNIS. The identification is used to uniquely identify the group of fragments of a single IP datagram. So when these all pieces come together in parts of the recipient, this identification will help the receiver to put them together, reconstruct the original datagram and pass it to the upper layers of the receiver. Now obviously some packets may be smaller in size, you may not need fragmentation at all, but some packets are bigger in size, you may do the fragmentation. So you have a set of flags to tell you that, to tell the receiver. First of all, first bit is 0, there are 3 bits actually here. So bit 1 is don't fragment, that means this is not to be fragmented, it's a single piece of data, it's a smaller in size, so no fragmentation was done, so that's the indication. This bit does, it is set to 1 if it is to be like not to be fragmented. And then bit 2 is more fragment, that means boss, this is not the first one or this is not the last one too. I won't say first one, but this is not the last one too. There are some more fragments coming, right? The next field what we are seeing is a fragment offset. So obviously we know that original datagram is there, the pieces are taken out of it one by one, chopped into pieces and sent to the recipient, right? So there are sent over the network. Now you have a particular piece, for example, a piece of fragment which is in original datagram has a position. It's actually at a specific position in the original datagram. Maybe, for example, 100 bytes away. I'm just taking an example. So there is a start of a datagram. There is one fragment which is say 100 bytes away from the start of the datagram. When this particular fragment is sent, that offset value is mentioned here. I don't know if you have played any time, I'm sure you would have played any time a picture puzzle, right? So that all pieces will be there and then you have what you call one by one you take the piece, you look at the piece, because we are all intelligent, human intelligent, you try to place the picture, a piece of that picture, that puzzle, and place it in an appropriate place, because once you put all the pieces together you get the complete picture. So you may pick it up randomly, right? You won't pick it from the left hand top to right hand bottom in a sequence. You lay a hand on the pieces, you pick a piece, look at it, you trust that that should occupy a certain position in the picture, you put it there. So accordingly, when you start putting it together, a picture happens. Now unfortunately, machines like host machines are not as intelligent as we are, humans. So it needs to be told very, very specifically. Boss, this is what you are getting a packet and this will occupy so and so position which is so many bytes away, okay, so many bytes away, so much bytes away, from the start of the original datagram. So when the receiver gets all these fragments, they may not get in a same sequence. So they keep on getting fragments. Looking at this offset value, they will place those fragments in the original datagram. By the time all pieces come together, the picture is complete. Right? So this helps to reconstruct the the original datagram accurately. So this is 13 bits and it specifies offset from a particular fragment relative to the beginning of the original unfragmented IP datagram. Right? Then comes time to live, very important. We are going to discuss this later also when I cover the trace route command. But fundamentally, the time to live is an information which will prevent the datagrams from persisting. So you have a packet coming into a router and then it forwards it, but somehow that packet is not able to reach the destination. There is some loop happens somewhere and then goes in a circle and returns back to this router or maybe some other router. Somehow it is taking way too long to reach the destination, or perhaps it is not able to reach the destination at all and is going in circles. Now as a network, this is not a good thing to happen. Some packets are going on circling. They don't have any purpose left in the end, but just adds to the network condition. So as a result, this field has been added to the IP header. So what happens actually is when a packet enters into a router especially, this TTL value is decremented by 1. Now the TTL value can change depending on the application. Some may use 64 as the initial value, some may use 128, some may use 256. It depends on that, or 255 rather, okay, depends on that. Now for example, if a particular packet comes with a TTL value as say 16, I'm just giving an example. It is received by the router, so router looks into the IP header and then say, hey, this is the destination, I'm going to forward to my next hop. So when it forwards the packet to the next hop, it decrements this TTL value by 1. So 16 becomes 15. Now this fellow goes to another router, so that router decrements it further by 1, so it becomes 14. So before it reaches the value of 1, because after 1 there is only a 0, right? The packet is expected to reach its destination by then. That means the maximum number of hops it would have gone through, it should not be touching a value of 1. Before that the destination should have reached. But in case it has not reached and a specific router gets the packet with a TTL value is equal to 1, what happens? The router drops the packet, because after 1 there is a 0. What it does actually, it says, boss, looks like you went through the network too many times, so I don't see any purpose in now forwarding once again to you or further. So I'm dropping this packet, I'm not going to forward you anymore. But before that, let me look into your header and then see who sent this packet originally, so the source address. So it reports back a message saying that, boss, your packet didn't make through the network, because it went through circles and I had to drop it because it has reached the maximum or the minimum TTL value. So that way, by bringing it down the TTL value every time one by one, you are actually ensuring that the datagrams are not persisting, they are not going in circles, right? Then comes the protocol. So the data portion of the protocol, the application protocol, whatever is being used is reflected here. So some sort of an early idea. Imagine in the recipient, when it goes upwards and reaches the network layer, though the job of IP layer is to ensure that it understands the destination address, and then if it matches with its own IP address, it passes it to the upper layer, right? While passing it to the upper layer, it has an early indication of what protocol this is following, the application, whether it's a HTTP, whether it's a telnet, whether it's a file transfer protocol, or maybe it's a DHCP or DNS, any of the application protocols. It's an earlier indication. So by now, we have just two fields left, source and destination address. By now, you know the kind of importance these fields have, right? So whether it's a version, length, or distinguished services, identification, anything you name it, they're pretty important. And if this header, any of those bits get corrupted, for example, there are any transmission errors, zeros becoming 1, 1 becoming zeros, then you are almost all processing a data which is corrupted, which could lead to a wrong forwarding or wrong decisions. So as a result, there is a error detection happens here, or error check happens here, saying that for the header alone. They said, okay, these are the kind ones and zeros that are being sent. The transmitter will add a checksum. It's like a signature. It sends the checksum along with within the header, so that the receiver, when it gets all these bits, header bits, it calculates a checksum on its own independently. And whatever it has calculated, the receiver, whatever it has calculated the checksum, it compares with the checksum that is sent by the transmitter. When both tally exactly, it trusts that the header has reached it cleanly. Exactly the way the transmitter has put together a header, that's how I received it. No bit got corrupted in between, there were no transmission errors, and it feels and it trusting that this is the good header which I can look into it and process it and use it to forward or pass it to the upper layers. And the final two portions are not much to explain. This identifies the the sender, what is the address of the sender, and the destination identifies the address of the receiver. So all in all, this is the header. So the most critical components, of course, destination and source addresses, but there are other fields also equally important to ensure that in the networking layer, the original purpose of ensuring that the packet reaches from the destination originates from the source, reaches the destination accurately, come what may. When I say come what may, whichever path it takes, right? Okay. So let's go further on to our discussion. So we'll go to what you call a simple concept behind routing. So you have a PC here, perhaps it has an address of 1.1.1.1. You have a PC here which is the destination, which is 2.2.2.2. Now obviously this PC from its application gets the details and realizes that the destination is 2.2.2.2. and immediately it makes a decision saying that this destination doesn't belong to my network because the destination address looks completely different from what I have, right? So what it does, it decides to pass it on to its next hop, which is nothing but the router. And that router interface, which is actually facing this particular network, is referred as default gateway. So while configuring the PC, apart from the IP address that you put together, there is a field called default gateway you will enter there, clearly instructing the PC saying that, boss, if you have any packet which need to go out of your network, here is the place you need to hand over. Of course, if it is within the network, then it reaches the destination directly. But if it has to go outside the network, then it has no choice but to hand it over to the default gateway. And how does it know which is the default gateway? That is a part of the PC configuration we do. So we already inform the PC where to send it in case the destination happens to be beyond the network. So as a result, what happens, it constructs a packet saying that source address is 1111, destination address is 2222. So this destination is reaching here. So as a result, what happens, this says forward it to R1. That's what the default gateway is all about. And when it reaches R1, R1 looks into the IP address and then say, oh, the destination is 2222, right? Let me hand over to my next hop, which is R2. Then R2 does a similar job. It says, okay, this is on other end of my, router network. So this belongs to this particular PC, which is in this network. So it forwards to the PC. So if you remember my post office example, this is the source, this is the hop number 1, this is hop number 2, and this is the final hop. Now, like in the post office, you may have many paths available. So here I have taken a very simple diagram. Okay, so it reaches the destination through alternate path as well. For some reason, for example, if this is broken, what will happen? The R1 adjusts itself in its routing table saying that I lost the connection to R2. Let me search for the next best path and forward it to R3 instead of R2. And it decided so by reading the destination address. So now R3 takes it and then forwards it to R2, and R2 does the job which has done earlier. A very simple explanation of the value and the benefit that gets added because of the the IP layer. Because each packet contains this particular addresses, no matter what path it takes, it reaches the destination, right? So let's look into the IP address, which is the most critical part of the IP header. So let's spend some time on IPv4 address to begin with. At the end of this particular session, I'll just touch upon IPv6 as well. So IP defines a network layer address that identify any host. So it's an identification of a host or a router interface, right? You saw the default gateway in the previous slides. It also identifies that. Any interface that is expected to receive IP packets must be configured with IP address. It needs an IP address. Any device without IP address, I'm afraid it is not identifiable in the network. So once it's not an identifiable network, it is not on the network. Very simple, right? I'm saying something which is probably very obvious to you all. So IP addresses are grouped together to identify a particular network or a subnet and are on the same physical network. In one of my introduction videos, I did said, right, there are two kinds of connectivity, user to user, network to network. So please see those videos once again in case you want to understand this easily. So obviously you have a range of addresses which identify a network. So all the host machines in that network carry the same network ID. So if you have another network, they belong to a different range of networks, okay? So to make the routing more efficient, network layer protocol groups the addresses both by location and also both by actual address values. So a router can list one routing table entry for each IP network or a subnet. So what happens actually is, imagine no matter where you live, maybe living in the US or India or any place, we identify any connection. For example, we have two large cities, okay, like for example, I live in Bangalore, so I take Bangalore, and there is a city called Chennai, most of you must be knowing, in south, right? Now there is a highway which connects with them. In US we call it as a freeways, we call it here as a highways. How do we refer that road? Someone, hey, what that road connects? They say it's connecting Bangalore and Chennai, two cities. Or maybe in US it is like San Francisco and Los Angeles or something, right? So the identification at that level, at an IP level, is all about networks, not individual addresses. We'll never say a specific locality in Bangalore and the specific locality in Chennai are connected through that road. We say that that is connecting two cities. So when it comes to the layer 3 or the IP layer, when a router has the routing table, it always identifies the networks by their network ID. That network may have many IP addresses, many host machines, maybe 10, 20, 100, you never know it. It never says I'm connected to all of them. Just say I'm connected to so-and-so network. On one end, other end I have another network. So that's the reason, if you remember my earlier introduction video, I said router is something which connects network to network, right? So you'll see more of it when I discuss the routing part later in one of the videos. So let's look at an IP address, the format of it. I think most of you must be knowing, but it's my what do you call, responsibility, or I would say obligation, to tell you everything in detail, so that later when you attend my courses, you don't have any confusion or any what sort of a gap in your knowledge. So a 32-bit number, which is an IPv4 address, is usually written in what we refer it as a dotted decimal notation. Okay. So a decimal part of the term comes from the fact that each byte, 8 bits of the 32 bits, is shown as a decimal equivalent. So we have a 32-bit number. It is split into 4 equal parts. Each part, which is 8 bits or 1 byte, is individually converted into a decimal, and they are separated by dots. That's why we call it as a dotted decimal notation. Like for example, 168.1.1.1.1, okay, 168.1.1.1 is an IP address, but written in a dotted decimal form. So if you want to see the binary equivalent of this, you need to convert each byte into a binary. Suppose 168 is nothing but 10101000, right? I hope you saw my numbering system video, right? So this is 128, the weight is 128, this is 32, 160, this is 8, so 168. These are simple to understand, right? There are 0001 and all that. So you have the 32-bit number split into 4 equal parts, and each part is individually converted into decimal value. So let's have a feel of this number. I know I might be telling something we obviously know, but again, it's important that we know exactly how the number spans out. What is the minimum number, how it spans out. So let's take an IP address which is perhaps the first address that we can use, like 1000. So the very next number possible is 1001. And trust me, these are all dotted decimal notation, and it progresses like that till it reaches 255. What is 255? 255 means in a binary form all 8 bits are 1. If all 8 bits are 0, then it is 0. So what's the next number? Next number is nothing but 1010. That means this 0 to 255 will again start all over from 0 again. Sooner or later it will reach 255, so this second digit will increment once. So the idea here is, for every 0 to 255, that is 256 numbers, the second digit will move by 1, get incremented by 1. Okay, so we have a 256 values here, we have a 256 values here, we have a 256 values here. If I go further, after 255 it touches 3, and soon it will touch 3.255, and then say 4.255, and continues further, right? And somewhere in the below you will touch a point where even the second one reaches 255, then the third one will move. So likewise, just have a look at it. It's a very simple setup, but normally whenever we are doing any planning activities, especially subnetting and all that, there could be a mistake here and there. It is not necessary that you may make a mistakes, but my experience tells that whenever things are very easy, mistakes happen there. Whenever you think that things are difficult, you'll be a lot more careful, and mistakes don't happen. The moment you start taking things easily, this is nothing, a simple incrementing, there is a chance of a mistake happening. That's the reason I'm just spending few minutes on this slide. So if you really see the progression, somewhere down the line, even the third byte touches the 255, right? And once it touches 255, then the fourth one will start moving. So here 1.255.255.255. Then this moves. Can you guess from 1000 to 1252525255525? What's the number of values you get? It's over 16 million values, right? So this is a 256. This is again a 256. That means every increment takes 256 values. So when does the third byte gets incremented? When both of them touch 255 to 55, right? That means 0 to 255 is 256. If you see the product, it is 65,536 values. So after 65,536 values, the third byte will increment by 1. Similarly, the fourth byte will get incremented by 1 when they actually touch 16 million values. And that's why if you go further and then finally touch the last value of all 255s, you would have seen over 4 billion values. Over 4 billion values that are actually lying in between the first value and the perhaps the last value. Just trying to make you comfortable with the dotted decimal notation and also how the number spans out. One more important information every host machine will be configured with along with the IP address is subnet mask. Okay. Now why the subnet mask plays an important role? For every IP address that you configure in a PC or a host machine, you need to configure the subnet mask along with it. And the purpose of subnet mask to tell the host machine that of the 32 bits that are there in the IP address, how much of it represents the network and how much of it represents the host. It's like the way you have a house numbers, right? Some of the addresses in India are very complicated. So you have a very long number in the beginning and they have a last number. For example, one of my addresses in the house where I lived was 17-1-178 by 91. Now that's a slightly longer number. What is my neighbor's number? 17-1-178 by 92, right? So what is common between him and me or that other neighbor and me? The first portion of the address is same, right? So we are all living in a particular complex or a housing complex. Major portion of our address is same except that the final portion, our apartment number, our house number is changed. So we as a human can easily identify which is the portion of the address that identifies uniquely our house and which is the portion which identifies the locality I am living in. But machines need to be told explicitly. They don't have brains, we need to tell. So subnet mask does that role. So in the subnet mask you are seeing ones here, you are seeing zeros here. And the size of the subnet mask is exactly like IP address. So you have 8 ones here, 24 zeros here. This means if this is 1, the corresponding bit in the IP address is a network bit. If it is 0, the corresponding bit is the host bit, which uniquely identifies that particular host in that network. So you have 8 ones here. That means all these 8 bits are network bits. And this 24 zeros identify that all these 24 bits in the IP address are host bits. So this is how it goes. So that's the network portion and that's the host portion. Okay. Why do you need this? Why I need to tell that? It's very important for a host machine to understand this part because then only it can understand where the destination is. For example, someone in my home, imagine I have a father and then not imagine I have a father, okay, who is no more. But imagine he gave a letter to me saying that, hey, why don't you post this letter? So it doesn't tell me anything. I look at the address of the letter and then say, okay, looking at the destination, somehow I realize that this fellow is next to my house itself. He's my neighbor. So the letter has happened to be, I need to hand over to one of my neighbors. But how do I know that address is in my neighborhood? Because I know my address very well, right? When I look at the letter and see the address, much portion of the address is exactly same like my own address except the last portion of it. So that way I identify the area identity, area locality ID and my locality ID is same. That means he is within my area. So I walk up to that home and hand over that letter to that person, right? But if I see the address entirely different and I realize that this letter need to go to some other place, what do? I go to a post office and drop the packet. So whether to post the letter which goes to another area or whether to walk over to my neighborhood and hand over the letter, that decision I need to make. Whether I do this or that. How do I know? First of all, I should know my address. Then I compare with the destination address. And if they are same, at least the area locality wise, then I'll walk up to that house and then hand over the letter directly. That my next hop is my destination. But if the address is different, then I depend on the postal system. So in our networking terminology, if the destination happened to be within my network, then I do a simple switching. Using the MAC addresses, I just simply switch and hand over, and the packet is given to the destination directly in one hop. But if I have the address different from my own address, then I do routing. I hand it over to the default router, the default gateway, what we saw in a couple of slides before. To make that decision, the PC or any host machine which is having the IP address need to know that what in my IP address, in my IPv4 address, which portion is my network, which portion is my host, so that I can make this decision whether to route or switch. Right? So that's the importance of the subnet mask. No host machine will accept an IP configuration without subnet mask. Your IP address configuration is incomplete if you don't add subnet mask. So if I take these both values and then convert into a decimal, like dotted decimal notation, this is how it looks like. So this is nothing but 20, this is nothing but 200, 195, 160, and I convert the subnet mask also into decimal. So 255000, right? Let's look at another example. And also I can indicate, I cannot configure like this. Configuration, I always need to present it as 255.0.0.0. But for my understanding and interpretation, I can just say /8. Okay? 8 means the first 8 bits are network bits. That's this indication. Let's look at another example. For example, here the value is like you have an IP address in a binary format, but in the subnet mask there are 16 digits which are telling that it's a network, and they are telling that 16 bits are hosts. So how do I do that? So this is my network portion, simple, and this is my host portion. So this host machine which has been configured with this kind of an IP address and the subnet mask, we are clearly indicating, saying that the 16 bits from your left side are network bits and the balance 16 is your host bits. So accordingly, if you have a destination address, compare the first 16 bytes with your own 16 bytes. If they are same, then trust the destination is within your network. If they are not, I'm afraid we have to send it to the router for the sake of routing, right? So if I now convert this into decimal, this is how it looks like. So you have 180, 150 which are equivalent of this IP address values, 195 and 165. The subnet mask is 255, 255, 0 and 0, right? And the number of networks being 16, you can refer it as /16. Okay, there are first 16 bits to the left side are network bits. One final example is like where I have 24 bits as a network bits and 8 bits as a host, and if I convert that into binary, into decimal, this is how it looks like. Hey, by the way, I think in my number system I clearly indicated why we need binary to decimal, decimal to binary, right? Simple. Machines understand nothing else but binary language, and we have a difficulty in understanding binary language. Imagine we discuss all the numbers and everything in binary. It sounds crazy, right? So we are comfortable with decimal. The machines are comfortable with the binary. So we configure in decimal, they interpret it as binary. So that number translation is a critical for any network engineer. And of course, being a 24 bits here in this example, we say /24, right? So that's the importance of subnet mask. Now, the IP address value right from the beginning to the end, the last value possible, may look for different sizes of what you call network bits, different sizes of host bits. In some case it could be 8 bits, some case it could be 16 bits, some case it could be 24 bits. How do you know which one is what? It is not a free-for-all situation, right? So what is the international body IETF, IANF decided actually is that, okay, we are going to set some guidelines and all of you need to follow that. You can't be, taking a private decision, okay, it's my will and wish, I take a particular IP address value and then make whatever subnet length as possible, number of network bits and host bits. So there are broader guidelines, there is good amount of flexibility given to you, but there are broad guidelines. The broad guidelines are the first 0000 is not to be used. In fact, if there is any packet with source address as 0000 means, it means that that host machine does not have any address. But if the first byte, and the division is done based on the first byte, 1 to 126, if the first byte goes from 1 to 126, okay, it is referred as class A. And these addresses are unicast. Again, in one of my fundamentals, I discussed unicast, broadcast, and multicast, right? What is a unicast? One sender, one receiver. And the rest 3 bytes can be anything between 0 to 255. So when I say X, it means that any 255. Now the guideline says that, boss, if it is 1 to 126, you should have at least 8 bits as your network bits. At least. You can have more. So there is a concept called subnetting, which I will discuss in a separate video. But you can have more than 8, but you cannot have less than 8. So 8 bits are basically the network bits, 24 bits are the host bits. Now there is a particular address called 127. It's a loopback address. It's normally typically used internal to any system. It's for many a times it identifies the its own protocol stack. There are many cases they use it to test their own protocol stack. So that is reserved for something within the system. It could be a router or switch or any other element. Internally, you have some IP addresses to be used to identify your internal entities, okay, different cards or blocks or backplane or forwarding engine, you name it. So that is not publicly routable. So this is not publicly routable. Then comes 128 to 191. So for these values, that means the first byte of the IPv4 address, if it falls between 128 and 191, the subnet length mask is 16 bits. So here you have 16 bits as network, 16 bits as host, right? And then you have 191 to 223, so which is nothing but again the first byte. And if this is the values, then you should have a subnet mask of 24 bits. And mind you, these are all minimum values to be maintained. In a class B, you can have more than 16 bits as network bits if you happen to do subnetting. Similarly, if it is class C, you can have more than 24 bits if you want to do subnetting, and same applies to class A. What follows next is a multicast addresses. So multicast address identifies certain groups, right? For example, if I have an OSPF routing protocol, so all the packets which are carrying an OSPF application on it, OSPF message on it, will choose a destination of 224005. For example, if a particular router takes it, it reads the destination address as 224005. It doesn't forward it in the sense, like a user packet. It say, hey, this is for me. There must be some routing advertisement or something. This is for my own consumption. So all the OSPF enabled routers will be able to process this packet. That means those routers which are enabled with OSPF, what we call routing protocol, belong to a specific multicast group, and they have been given one specific IP address. So likewise, there are other values. So you have for EAGRP another routing protocol. So you have different protocols, groups that are available. They are all identified by a specific multicast address. So whoever takes it will pass it to their peers, there are other members of the group. And of course, last 242 to 255 are again experimental, they are not in use. All in all, we are looking at three ranges, class A, class B and class C. They are all unicast addresses. And each of them have a different subnet length mask, okay? Different lengths of subnet mask. Class A, it is minimum 8, class B, it is minimum 16, class C is minimum 24. So that's how the classification has been done. For example, let's look at some of the examples. For example, I take a class A. So there is a network ID. So the very first value, for example, this is the network portion, this is a host portion. what you are noticing actually is all the host portions are 0, right? So trust me, if you have a network ID and all the host bits are 0, that is nothing but referred as a network ID. And when all are ones, for example, for the same network portion, if you have all the host bits as 1, it's a broadcast address. One value above the network ID is the first usable address, which can be assigned to a host machine in this network. And the last usable address is one below the broadcast address. So 1.255.255.254, which is very, very clear that 1.000 and 1.255.255.255, these two values for this network should not be assigned to any host. Let's look at what you call class B address. So that's the network portion, right? Then the class B address, this is the network portion because it's a minimum 16 bits. Again, when the host bits are 0, this is an ID. And when host bits are all ones, this is a broadcast address for this network. So the first value is 01, which is one above the network ID, and the last usable address is 255.254, which is one below the broadcast address. So you see the class C address, this is like 195, 110, so obviously here 24 bits are the network portion. The host bit is just 1 byte. Nevertheless, because all are zeros here, it is a network ID. And here all are ones is because of broadcast address. So simple way of identify classification is look at the first byte. Subnet length can be anything, but minimum are these values, by the way. It can be 8 or 16 or 24. But the way to identify the classification or which class address belongs to is by the first byte only. Okay, that's the only way, right? So if I focus on the unicast address, other addresses doesn't interest me at this moment. Some of them are to my interest at a later stage, but at the moment my focus is which are those address values which I can assign to host machines, and we'll compare them to class A to class B to the class C. So I've just reproduced what I discussed in the slide before the last slide. If I see, if I am allowed to have only 8 bits in my network as a class A, and looking at the values that are allowed in class A, how many networks are possible? 1 to 126. That is nothing but 126 networks possible. How many host bits are allowed? 24 bits. So if I really see that number spanning out in one of the slides we discussed, right? The number of hosts per network in a class A, and if you have not subnetted it, it is limited to 8 bits only. It is 16,777,214 addresses possible. Quite huge, right? Can you imagine any subnet or a local area network with that value? No. So that's the reason subnetting becomes that much more important later. If I go to class B says first 16 bits are networked, right? So obviously there is a bit of a balance here. The number of bits are in network and the number of bits in the hosts are same. But looking at the values allowed, if you really count 128 to 191, it is 64. Okay. So don't just subtract it. It will come in 63. That's a mistake many people make in my classes actually. So if I really count from 128 to 191, both inclusive, it is 64. So 64 values are allowed in the first byte. 256 values allowed in the second byte because I can go from 0 to 255. So as a result, 64 into 256 results in 16,384 networks possible. Obviously, since we are giving more bits to the network, more networks are possible. Since we are giving lesser bits to the host, it is way less than what we saw in class A. So here we have 65,536 values are possible. Okay. Now, if I go to class C, it is somewhat opposite of class A. Here the 24 bits are network bits and 8 bits are host bits. So as a result, you have 2 million networks possible. If I take this one, this is 32. 192, 223, if you count them, it is 32. 32 into 256 into 256, you get 2097152. And the number of hosts are lesser. Okay, so it is 254 actually, 254. 256, but two values will go, one for the ID, one for the broadcast address. In fact, this is also 65,534. So my apologies for that mistake. So this is 534 actually. right? So that's how they compare. So idea is very clear. If you want more networks in an organization, go for class C. You want more hosts per network, go for class A. If you want to somewhere in between, go for class B, right? So that's how they need to be followed, and there can't be any exception to this. I spoke about subnetting. There is a full video later, but let me just quickly introduce you subnetting. For example, I take an address which is perhaps class B address. Okay. So 10010110, that means this is 128, this is 16, so it is 144. So 144 plus 4 is 148. Okay. And 150. So this is 150 means the first byte tells that it's a class B address. Traditionally, a classful address should have 16 bits as the network portion, but I am adding 3 more bits. That means the host values, whatever I have, I am subdividing it, I am dividing it. As a result, what happens? My network portion is not limited to 16 bits, but it goes to 19 bits. So 8 here, 16, 16 plus 3, 19. And accordingly, my subnet mask also changes. So how does that change? It changes to 255, 255, 224. If I really see the decimal equivalent of this byte, it is 224. Now I can't do that because I feel that 16 bits in a network is way too high. 65,534 hosts is way too high. Okay, so I can subdivide them and then save buying new addresses, from the internet service provider. So there is a full video on the subnetting. So I suggest you go through this. That video follows after this video. So I have spent some time exclusively on IP subnetting. So please do follow that, because subnetting is something which is important from your job point of view, from CCNA exam point of view, for any other evaluation you may be facing in your career, right? So there are some fundamental rules, IP addresses, and and that rules need to be followed strictly. So in this example, I am looking at 3 networks, right? This is one network where all the hosts share one particular identity. There's a second network, so it has its own identity. And there's a third network. Even a router-to-router connection, which is a wide area network link, even that is a network where I have 2 users. Both the router interfaces are the users themselves. Rule number 1. All IP addresses in the same group must not be separated by a router. If I have many of the addresses starting with 1, then better they be on one side of the router in one network, right? And the second rule is opposite one, okay? So IP addresses separated from each other by other router must be in different groups. So I can't put this 222 here in 1111. A classic simple example is you lived in certain place, so you have an address which is local, right? For example, I lived in a city A where I have a particular address. Because of something I shifted to another city, city B. I need to take city B address, right? I can't say that I like that address in city A, let me use that in city B also. It doesn't work out, right? So if you use, what happens? You are not connected. Anyone posts a letter to your address, it will go to city A, it won't reach city B. It is as simple as that. It's a very trivial matter, but I'm just emphasizing that. That means addresses that are allocated to this network should be used here only. Addresses allocated here must be used here only. If they are different, then a router has to come in between, right? To identify them as separate networks, right? So last portion is IPv6. I know it's slightly longer video, so thanks for watching so far. Just few more minutes, I'll complete IPv6 and we'll conclude this video. IPv6 much bigger format, right? For example, it is a 128-bit address. IPv4 was 32-bit address. This is 128-bit address. Look at the comparison. An IPv6 is a 128-bit IP address, which is over 10 power 28 times as many addresses as IPv4. And to migrate to IPv6, all the routing protocols need to be upgraded. There are many funny, geeky examples to make people understand how big IPv6. And there is one example which I honestly say I took it from another video, which I thought is a better way of explaining the size. The story goes like this, that a person goes to an ISP who happened to have all the IPv6 addresses with him, saying that I need some IP addresses though. The ISP asks, okay, how many you need? this fellow says, I need the complete IPv4 capacity, which is about 3.7 billion. Trust me, 3.7 billion addresses are possible in an IP4. I need so many. So ISP obviously thinks, right, this fellow is absolutely crazy. What will he do with so many addresses? But anyhow, he's paying money. Why should I object? This is a weird story, so just bear with me on that. So he hands over IPv4 addresses to this guy, 3.7 billion. This man happily walks away, only to return later saying that somehow I exhausted all those addresses. Give me a fresh set of IPv4 addresses which are 3.7 billion in size. The ISP thinks this fellow is now really mad. But what do I lose? I give it another one. And this fellow keeps on coming and taking fresh and fresh set of IPv4 addresses. Now the question is, if this ISP somehow hypothetically has the entire collection of IPv6 addresses with him, and if this customer, this crazy customer, comes again and again to this guy, and if he comes, imagine every second, okay, every second he returns back and takes a fresh set of IPv4 addresses, how long this particular ISP, Internet Service Provider, can keep on giving fresh set of 3.7 billion addresses every second? How long he can give? Any imagination, any guess how much time he can support before he completely exhausts IPv6 addresses? The answer is 400 years. Sounds crazy, right? That's how the IPv6 is. So 400 years into 365 days, I'm ignoring leap years, okay? Just for the sake of it. 400 into 365 days into 24 hours into 60 minutes into 60 seconds into 3.7 billion, which is IPv4 capacity. So it's to the stretch of imagination. I don't think we'll feel a shortage of IP addresses if you are deploying IPv6 address. That huge. Looks like the IPv6 was created with vengeance. Okay, that IPv4 they thought they'll never exhaust, but they got exhausted. We felt shortage. Of course, thanks to network address translation, port address translation, we managed it. So when they made IPv6, they said this should not exhaust. So we'll see. It should not exhaust theoretically at least. But unless until we spread our network to the entire universe, we don't know. Okay. But for the moment, it all looks okay. So that's how gigantic and huge IPv6 is. So let's look at the header. So header is no basically brainer here. It looks quite similar to the IPv4. Thankfully, the size is same almost. Okay. So the 4 bytes is there, but the address is 16 bytes. Remember, it's 128-bit address. So let's look at the components here too. Version tells that this is an IPv6. There it said IPv4. Now we say class is actually is traffic field is the same size, performs same functions, takes on same values as type of service in the IPv4. You have the distinguished service, right? So that's like class here. Flow label is a 20-bit flow label, can be used to instruct a router to use a specific outbound connection of a traffic flow. So in terms of forwarding, it suggests that. By having all packets in the same flow use the same connection, probability of packets arriving at the destination out of order is reduced. So there's a bit of an instruction within the header, boss, why don't you use that so and so connection, the outbound connection. When you're forwarding, why don't you use so and so connection? So that when all these packets, sometimes hundreds and thousands, for all even millions, if it's a huge file that is getting downloaded or uploaded or whatever is it, they all come in a specific order. Going out of order is now becomes bit rarity. Okay, you are reducing that situation. Payload length, it indicates the payload being carried by the IPv6 packet, the user data. Okay. The next header field, similar to the protocol field, okay, in an IPv4 header, indicates the type of header encapsulated in an IPv6 header. So what is the application level? So typically it's an 8-bit header, indicates a specific transport layer protocol. Then you have a hop limit, something like what we discussed in TTL time teller, going in circles. So 8-bit hop limit replaces and performs the same function as an IPv header TTL field. Specifically, it is decremented at each router hop until it reaches 0, where it is discarded. And of course, you have nothing really new here. Source address identifies the sender and the destination identifies the receiver. So lesser components, more or less the purpose is served exactly like what is there in IPv4, happens here in IPv6 also, right? Look at the format, and I think I discussed this in my numbering number systems in my earlier video. 128-bit, obviously it is very, very tough to see it in a binary form. It looks absolutely crazy for us. Even decimal looks absurd, okay? Decimal looks also very big. So choice is only hexadecimal. So you take entire 128 bits and divide it into 8 parts, and each part is 16 bits, right? So if you are good in mathematics, 16 8s are 128, right? So if you do like what do you call 8 parts, each is 16 bits. Out of those 16 bits, 4 bits are converted into a specific hexadecimal value. For example, you see 1010. This one is not a binary, yeah? It's a hexadecimal. So it is 0001. This is a value. Similarly, 0 is 4 zeros. So they are not decimal, they are all hexadecimal. And again, 1 is 0001, 0000. That means this is 16 bits, each of them representing 4-bit binary. For example, I take ABCD. A is nothing but 1010, right? B is nothing but 1011. C is nothing but 1100, and D is nothing but 1101. So likewise, each quartet represents 16 bits, 4 into 4. And together they represent 128 bits. And each quartet is separated by a colon. That's how the format. Remember, in IPv4 we use dot. Here we use colon to separate them. And this is how you interpret it. This is how you configure it, right? But still looks huge, right? Even if I have, like, for example, 8 quadrates into 4, I'm looking at 8 4s are 32 hexadecimal digits. Still it could be slightly painful to configure and understand. So thankfully IPv6 allowed some abbreviation. You can shorten it. Okay. So how do you shorten it? For example, if I'm seeing an address here, I'm seeing FE00000000 like that, right? The first rule says, please ignore all the preceding zeros in every quadrant. For example, if this is 0001, it becomes 1. There are 0000, it becomes 10. If this is 0056, it becomes just 56. The first abbreviation in terms of shortening the length of the IP address is by ignoring preceding zero, which we also do, right? For example, I'm holding a pen in my hand. Someone says, Samba, how many pens you have in your hand? I say 000001 pen, which means 1 pen only. All the preceding zeros have no value. So likewise here, all the preceding zeros can be ignored, and the host machine which is taking this address can easily understand. So as a result of that first rule, the IP address is reduced to this. So FE00, you have 10, 101, 000, and 56. Now there is a second rule. Second rule says that if you see two or more consecutive zeros, that means quadrats being zeros, you can replace them with a double colon. Now you can have a situation where that is happens twice. Here also you have 2 zeros, here you have 2 and more. Which one to do it? You need to do only one, you should not do double. So you take the longest consequences of zeros, which should be at least 2 or more, you replace it with double colon. So suddenly an address like this is reduced to FE00001 double colon 56. Lot simple, right? And like I said, when things are simple, mistakes do happen. Okay. And here are some of the mistakes that can happen. Let's take the same address what we took in the previous slide. Someone happily ignored the succeeding zeros. You should only ignore the preceding zeros. So that's a mistake, right? Someone used it double colon twice. I said, I have 2 zeros here, I have 3 zeros here, let me do it both. The problem actually is when a host machine gets this IP address configured, it knows that there have to be 8 quadrats. And you have given 3 there. That means there would be 5, which are zeros. Now it doesn't understand whether to put 3 zeros here or 3 zeros here. That's the confusion it will have. So as a result, you use the double colon substitution only once. So you have FE00 colon 0 colon 0. Don't replace with double colon here. Take the longest and put a double colon here. So now the host machine gets 1, 2, 3, 4, 5 quadrats. So it knows the total should be 8 quarters. Because of the double colon, it puts 3 zeros in between. And wherever it sees 2 digits, it happily adds zeros before that. Or if it is like 1 digit, happily add 3 zeros before that. Okay, 0, 0, 1, they all will be added 3, 3 zeros. So thankfully, in the beginning, the IPv6 format length scares us, but thanks to this abbreviation, perhaps it's a lot more easier to use it compared to IPv4. There are many more advantages with IPv6. Perhaps when you attend my classes, I'll cover some of them, especially how you can configure an IPv6 address in a host machine or a router. Lot more options in terms of assigning IP address compared to IPv4. IPv4 has only static and dynamic. So in IPv6, we have a static configuration, dynamic configuration, auto configuration. There is another method called EUI64, which I'll cover it when I'm covering the routing part. Okay. So IPv6 routing sounds similar, except that the address length is different. So you have an IPv6 address here. By the way, this is a link local address. I'll talk about it later in the IPv6 part. Okay, when I'm discussing routing. So this fellow has an address, destination also has an address. So what will happen now actually here is you see here 23441111 AA 1. This is same thing but 2. That means there are different networks. You say double colon here, I got 5 quarters, that means there are 3 zeros here. Similarly, there are 3 zeros here. So what happened? There is an address, so source and destination address, the IPv6 header will take it, and put those values in that. So obviously it forwards to R1 and then goes to R2 and then finally reaches the destination in this example. In principle is exactly same, right? So that's how IPv6 goes, okay? So we have seen today a network layer, we spoke about the IP headers and then we spoke about what you call the format of an IPv4. We saw the classification of IPv6 IP addresses. We saw a bit of subnetting. There is a full video coming later, you can watch that. And finally we looked at an IPv6 and then saw what a huge length it has in terms of the number of values it can accommodate, right? So that's about the IPv4 layer, okay, or IP layer rather. So thanks for watching. You can watch this video several times if any of the topics are not clear to you. You're most welcome to write to me, okay, for any queries, okay. So, but since you are going to be my future student, I'll see you on online courses or perhaps even in the classroom where I can take any questions on the topics which I covered today in the session. Okay, thank you and see you in the next video.